the road and finish talking about orbital hybridization. But before we leave this is something that you're going to want to know for your Lewis structures tomorrow, in addition to orbital hybridization. So we did this. Actually, this is not quite the final Lewis structure. This was like, I think it's step 4 on your steps to draw a Lewis structure tomorrow. The reason this isn't a final Lewis structure is because the carbon only has 6 electrons around it. This is the step right before the last. And I said that you can swing a pair of electrons, lone pair electrons, from either oxygen. We just happen to swing it from the north oxygen. So by swing, I mean you take lone pair electrons, you bring them down and make a pi bond between the central atom and that terminal atom, and then that carbon has 8 electrons. Both oxygens still have 8 electrons. But there's this idea, you might be, well, like Mrs. Snipes, why didn't you take it from the other one? And I could have. And that brings us to a concept of resonance structures. So if you, and you're going to run into this tomorrow, where you need to go ahead, your central atom doesn't have 8 electrons, so you need to swing lone pair electrons in. Okay, so you have options sometimes. In this case, both options were equally awesome. Okay, so resonance structures are basically the same, are very similar Lewis structures, but you draw in lone pair electrons to make a pi bond from 2 different atoms. Okay, so in this case, this was the structure we left with on Monday, but of course we also could have done this. Okay, it's like, am I seeing things? And I said you could isotopically label those oxygen atoms to know which one is which. And they are different. They totally are different. Well, not totally are different, but they're great possibilities, okay, of the formate ion. Okay, so if you have a pair of structures that are equally awesome like that, actually what happens is, and I kind of think of, I might have said this to you guys before, but if you take a pop bottle, a glass pop bottle, and you wet your finger and you kind of go around the rim, you get kind of you can actually get a resonance tone from it. Okay, that to me kind of reminds me of resonance structures. Basically what happens is those, the electrons that are participating in that pi bond, they actually kind of buzz, and both structures are like, really? I'm like, really? Okay, so these electrons here, these 2 electrons that are in this pi bond here, or in this pi bond right here, they are what we say delocalized. They kind of buzz around. Delocalization is an awesome thing. So what you get with, in this case, with those 2 resonance structures in the formate ion, is you don't have the left one, you don't have the right one, you actually have something kind of in between. So that's what this is trying to tell you. You don't have the left one, you don't have the right one. What you really have is something in between. Okay? So I mentioned delocalization. Electron, those pair of electrons are delocalized. It's almost kind of like dislocated, delocalized. Okay? They kind of buzz around. The coolest example, and I didn't bring my little stick ball model of it, but the coolest example I know of delocalized electrons is the benzene ring. Okay, so the formula for benzene is C6H6. Okay, and it's a ring structure. So basically, I used to be better at this than I am. I'm going to try to draw 6 carbons, okay, in a ring. Okay, is that 6? I think it is 6. And then there is a hydrogen on each carbon. Now, if you're looking at the number of electrons around each carbon, you're like, hey, Mrs. Snipes, that's not quite right yet, because they only have 6 electrons. So the benzene actually does this, where you have alternating double, single, double, single, double bonds. Is that not awesome or what? That's a benzene ring. But honestly, those 6 electrons in those 3 pi bonds actually delocalize, and that's what makes this benzene ring just awesomely, wonderfully reactive, and okay, it's a crazy molecule. So I could draw another resonance structure, basically kind of showing it the double bonds alternating at the alternate carbons. But there you go. So resonance structures. But now, not always can you, and usually it's that central atom or the middle atom that you're trying to get the complete octet for at the end of drawing your Lewis structure. Not always does a resonance structure make as much sense as others. Obviously, you want to swing so that you give everybody complete octet, like we did with formate. Okay. You want to, if you do have a charge, like in the case of the formate ion, we ended up with actually a charge on the oxygen atom. If it does happen like that, where you have extra electrons here or there, it needs to be consistent with that atom. So for instance, oxygen is a non-metal. It tends to be negatively charged, so that makes sense. And actually on either Friday or Monday, we'll get to something called formal charges, and that kind of shakes out there too. The other thing is that, let's see, if you do have within your final Lewis structure of your possible resonance structure, if you do have a charge separation, let's see, structure plus separation, okay, you want to have less of a charge difference as possible. This last one, this is what you're going to run into in tomorrow's lab, okay? We said that if it's a neutral molecule, which formate is not, but if it's a neutral molecule, you can know how many times it's going to reach out, the expected valence of an atom. We said the expected valence of an atom is 8 minus the group number. That's how many sigma and pi bonds it's going to reach out. So that actually goes for this example right here. Carbon dioxide, actually, we could, from our pot of valence electrons, we could either go this route, okay, or we could go this route with the same pot of valence electrons, having a carbon atom in the middle and 2 oxygen atoms, scooting out. And by my count, a complete octet is satisfied for all 3 atoms in both cases. Most students would say that A makes a lot more sense. We go with symmetry, okay? And you're right, we go with symmetry. But the other thing is, let's look at the expected valence of oxygen. How many times will oxygen reach out? Well, oxygen is a 6A, so 8 minus 6 is 2. So we expect it to reach out twice. By reaching out, I mean sigma and pi bonds. So we have oxygen reaching out twice. Then over here we have oxygen reaching out once and reaching out 3 times. And so, okay, so to me, it's that kind of last criteria that kind of fails there. Okay, so that's what we're going to pick up later. Now, oy vey, go back to, it's on the second page of part 8, actually. We're going to come back, the first part of part 8 talks about bond characteristics, and we're going to come back to that. Okay, so hopefully you can find something that says orbital hybridization. Everybody find a segment that says orbital hybridization. Awesome. Okay. Very good. Okay, here we go. Hybridized orbitals. Hybridized orbitals. Now, one of the things, and I was thinking about this, I haven't thought much about it until, it's funny how you teach something for years and years, and you're like, oh, well, that's how that, or that's how I can explain this. Hybridized orbitals are basically one atom that is taking some of its own atomic orbitals and hybridizing them to make different hybridized atomic orbitals, okay? Because, we've talked about bond orbitals, and that's coming up again, too. Okay. So basically, when it says orbitals formed from combining S and P orbitals to produce orbitals that are neither S or P, okay, that is one atom taking an S orbital and one of its P orbitals, put them together, and spitting out hybridized orbitals, okay? So the types of hybridized orbitals we're going to talk about, I'm going to focus really for sure on 3 different scenarios that an atom can do. And there are 2 kind of other scenarios in the wings, okay? of what an atom can do to hybridize orbitals. And it's like similar to like genetic hybridization in that if you have P's, you can take, your parents and you end up with your child has characteristics of both parents. Okay, it's very similar in that sense. Another thing, and actually we call this the top one, we call that the conservation of orbitals. So for instance, if this atom is going to take one of its S and one of its P, it's going to only have 2 hybridized orbitals from that. If it's going to take, another scenario is one of its S and 2 of its P's, okay, 1 plus 2 is 3. It's going to have 3 hybridized orbitals, okay, that sort of thing. Okay, and then the other thing kind of goes back to genetics. It's like, well, the final hybridized orbitals are products of the parent orbitals, so they have to kind of fall into line with regard to both shape and energy. And I'll kind of show you how that looks. Okay. Now, a cool thing, and I don't know much about genetics, or if this kind of falls apart with the parent plants and then the child plant, but the hybridized orbitals that are spit back after hybridization are all equal. Okay, so this is kind of cool, and actually there's evidence of this, and that's just kind of how we came up with this concept of an atom hybridizing its own atomic orbitals. So now this is an important concept. We've talked about when an atom goes to join with another atom to make bonds, okay, those hybridized orbitals are specific only for electrons that are participating in the primary sigma bond and lone pair electrons. What that leaves out is these hybridized orbitals will not participate in that secondary pi bond. Okay, so hybridized orbitals, sigma bonds, and lone pair electrons. That's it. For the pi bonds, actually those are going to be the atomic p orbitals that are going to overlap between the 2 atoms to where the electrons are going to reside. And you can almost see that because p's are those lobe ones, okay, and definitely make more sense than the s. Okay, so I mentioned 3 and then 2, and actually this slide shows 3 and then 2. So the 3 where we're going to focus on tomorrow are these first 3 types of orbital hybridization. In the first case, an atom has taken one of its s and one of its p. Okay, we call that sp orbital hybridization. Okay, and it gives 2 hybridized orbitals. The next one is, again, it takes one of its s and then 2 of its p's. We call that sp2 orbital hybridization. The number of equal hybridized orbitals will be 3. And then the last one, again, we're going to hit hard tomorrow, is where an atom has taken its atomic orbitals, one of its s and 3 of its p's. So it's going to have 4 equal hybridized orbitals. We call this sp3 orbital hybridization. The other 2 that are kind of lurking, okay, and we need to kind of know them at least a little bit, okay, they involve then not only S and P, but then they bring in a D. So we have sp3d and sp3d2. Okay, again, this is a single atom hybridizing its atomic orbitals to spit out these hybridized orbitals that can participate in sigma bonds and lone pair electrons, or a location for lone pair electrons, an electron domain. Okay? So the conservation of orbitals, all it means, and if you get stuck, you basically add the superscripts. Okay, so we add these 2 superscripts, and we get 2. Okay, we add these 2 superscripts, and we get 3. These 2 superscripts, and we get 4. Okay, these 3 superscripts, we get 5. These 3 superscripts, we get 6. Okay? All right. Okay, so in science, it's all about building on observations. So honestly, I'm going to try to prove to you that if an atom didn't hybridize its orbitals, we would not observe what we observe. So I only have one example to show you. The example I'm going to pick on is methane. So methane formula is 1 carbon and 4 hydrogens. Okay, this could be our methane molecule right there, and actually have something kind of similar here. So you're like, well, how does that show that that carbon atom that's connected to 4 hydrogens has actually hybridized one of its S and 3 of its P's to spit back hybridized orbitals that can sigma bond to those hydrogens? How do we know that? Well, it has happened. I'll try to kind of prove to you, maybe in just a couple slides, why we know that's the case. First off, we know, and this is amazing, but you can actually break bond after bond. And again, you can isotopically label your methane, okay? But we can test each of these bonds, okay? They are the same in energy, bond energy, and we're going to talk more about that later in the first part of 8. They're same bond energy and bond length. These are identical bonds. Right, okay. So if we look closer at what a carbon atom is, okay, a carbon atom has 6 electrons. That carbon atom has 6 electrons, and these are how its 6 electrons are configured. Remember that, clear back with Bohr, and then, of course, Schrodinger, we know that an electron is assigned an orbital with a specific energy and a general location. So those 6 electrons are configured this way. Right. Okay. So, and remember that when it does this covalent bond here, okay, and this is just how it works. You know, a hydrogen only has 1 electron, so probably it's got one of the electrons here that's a pair of electrons, and the carbon atom's donating 1 electron. So how in the heck is it donating or sharing 4 equal electrons? When you have your valence electrons, you have 2 electrons in the 2s and 2 electrons in the 2p. Well, we know that an excited electron configuration of carbon would be this, where basically 1 electron is jump shipped from the lower energy 2s up to the 2p. Okay, actually I think I'm going to kind of piggyback on that. But even so, these p electrons would be unique from that electron there in the 1s. I feel like I'm some sort of magician trying to bring you up to. Okay, so let me show you from this excited state, from those 4 valence electrons of a carbon atom, it's 4A, 4 valence electrons, what it does when it basically hybridizes and comes up with remember the third, on the first 3 that we came up with, that was sp3 orbital hybridization. This is actually what I'm going to show you. All right. I thought that was too good to be true. Well, I'll try closing this out. Should make a difference. My kids say, Mom, you have too much open. Maybe. I'm going to look over your shoulder again and why that's coming up. Are you where we were?
Yeah, right here.
Oh, awesome. Okay, cool. Okay, look at it. Okay, yeah. Just a bunch about the same thing. How funny. You are evil. Okay. Yes. Maybe it's being shy. Done with that too. I've invented a new word. It's called technology redundancy. So, but there are certain things that you cannot be redundant for. This is probably one of them. plug this back in. Well, let's just go on. I don't know. The next, you see some figures about methane. You see some figures about actually, if this is hybridized, 3 of its P's and 1 of its S, remember the shape of P's? They're a dumbbell shape with the nucleus at the center, basically an electron cloud. So the S, if you have sp3, it's high in the P, low in the S, so definitely we have this low shape thing going on. So that's, hopefully, maybe you can see in the figure of methane, the only atomic orbital that the H's, the hydrogens have, are the 1s. So basically we have a spherical region that is overlapping with the sp3 orbital hybridized carbon. The next one actually kind of goes back then to the sp2 orbital hybridization. And in that case, just like it sounds, an atom, this is an example of a central atom that has actually taken 1 of its S and 2 of its P's, okay? Due to the law of the conservation of orbitals, those 3 orbitals hybridized to create 3 equal hybridized orbitals. And remember that actually these hybridized orbitals can participate in sigma bonds, but they can also participate in lone pair electrons, or lone pair electrons can actually be buzzing in that electron domain. The last one is sp2, or sorry, sp orbital hybridization. This orange atom has taken 1 of its S and 1 of its P's, and it has actually hybridized those 2 atomic orbitals to spit out 2 equal hybridized orbitals. These are both sp hybridized orbitals. Okay. So that's what we have there. Are you serious? I think it's done for the day. It just is. Is this Monday?
PowerPoint has died.
Okay. The next slide. Oh, good. Okay. Now we're along to something. You see the V, the Vesper. I pronounce it Vesper, but really it's VSEPR. Okay. You can see the acronym for Vesper stands for valence shell electron pair repulsion theory. Now remember what we learned about theories is theories are not just a guess. Okay, theories in science are actually, this is a theory in chemistry that has come about from scientists putting the pieces together. But if you break it down, we know what a valence shell is, right? Those are the special electrons in the highest N, okay? Valence shell, electron pair. So here's my thing. We've been kind of talking about pairsies, where anytime there's a sigma bond or a pi bond, they go in pairs. For the most part, lone pair electrons go in pairs, okay? So valence shell, electron pair, repulsion. Now, here's the deal. As I've held these up, and I might need to convince you about it, but if 4 things wanted to scoot or repulse away from one thing as much as possible, this is actually the shape they would form. So valence shell electron pair repulsion theory is a way to know what sort of shape you're going to get from your atom that's undergone that particular orbital hybridization. This is sp3, this is sp2 shape, and this is sp shape. Okay, actually we call this structural geometry or electron pair geometry. Okay. So as we talk about this shape, okay, we are talking about the shape around a particular atom. Okay. Now there's a slight difference, and I don't know how much time I'll spend on it in Gen Chem 1, but there's definitely a difference between the structural geometry, the shape around an atom, versus the shape of the molecule. They're totally different cats. Okay, and your textbook actually kind of has a slide coming up that kind of looks at both the structural geometry of an atom and the geometry of the simple molecule. Sometimes they're related, sometimes they aren't. I think I'm going to just turn this stupid thing off. I just am so So, actually that kind of brings us up to, I'm looking at page 5, and we're kind of near the bottom of page 5, if you believe it or not. The bottom of page 5, there are 2 tables. The table on the left actually is the one that you're going to use for tomorrow's lab. Okay, on the left, I'm tempted to just throw this thing out the window. I'm not going to do that. On the left, actually, you see 3, I call them 3 rows, okay? And the 3 rows correspond to the 3 major types of hybridizations that I just pointed up here. Let me go ahead and unscramble them. Okay, this would be the first row, okay, where an atom has undergone sp orbital hybridization. The geometry around this orange atom actually is linear. I like to call it hot dog, but actually it's linear, okay? And the bond angle, okay, is 180, like that, okay? And again, this is the valence shell pair repulsion theory. Anyway, the R stands for repulsion, okay? So this is the farthest apart they can get from each other. Okay, so this is sp2, orbital hybridization. And actually we call this, does it look like it lies in a plane? It does. And it looks like 3 Z's. Okay, so we call it trigonal planar. So this is trigonal planar. This is, again, the geometry around that atom. It's not necessarily the geometry of the molecule. Okay, this one, we call this tetrahedral. Kind of reminds me of like a pyramid, I suppose. Okay. The bond angle you see in your little table. This bond angle, if you take a circle and divide it into 3's, you get 120. Okay, so 360 degrees divided into 3. Okay, so this is 120. Okay, and this actually is 109.5 degrees. I used to say, well, that's a great, that'd be a great frequency for a FM radio station, and somebody's like, hey, they don't go up that high. So I'm like, oh, okay. So 109.5 degrees. Okay. So that kind of brings us to the last slide on the bottom of page 5. Okay. All right. So that slide on the bottom of page 5, the last slide, you see the SP, SP2, SP3. Then you also see the other 2. If you want to, and I'll put this up on the slide on the. Yeah, it's like, you sure you want to start? I'm like, yes, please. For the other 2, the SP3D and the SP3D2, I know later on it mentions it, but if you want to go ahead and put expanded valence, you can. Okay? Remember we said that any atom that is beyond period 3, which is a bunch of elements, any element beyond period 3 actually can form an expanded valence when it's bonded in a compound. I'll go ahead and, there's not a column for this necessarily, but let's see, I'll put number of electrons, okay? Instead of 8, guess what? This sp3d atom is going to have 10 electrons around its atom. And do you see why there's 10? Because you have 2 electrons, or you have 5 hybridized orbitals. So number of orbitals, 5 and 6. Okay? So that's why you basically have 10 electrons around this one, and you have 12 electrons around that one. Ready for the password?